inside a bearing is allowed to drift from perfect roundness by less than 1/10 of a micron, 300 times finer than a human hair. A hydraulic cylinder 22 meters long holds 700 bars of working pressure without leaking a drop. That tolerance exists for one reason. Every cylinder, valve, pump, chain, and gear in heavy industry runs on motion systems the eye never sees. The components that fail decide whether mines, refineries, and grids stay up. Let's open them. Every pipeline, every refinery, every pumping station depends on a component that gets almost no attention until it fails: the valve. Brass valves used across hot and cold water, HVAC, and fluid control systems begin as rough forgings or castings fed into heavy-duty machining units. Rotating tools cut internal threads, smooth rough edges, and mill the connection points needed for an airtight seal, leaving reflective brass components with clean threading. Workers then assemble internal subcomponents, stems, gates, sealing rings, at conveyor stations before pneumatic presses and automated screwdrivers secure these cores inside the outer body. Handles and lock nuts follow at dedicated stations. Inspectors operate every finished lever by hand to confirm smooth rotation before the unit reaches pressurized testing, where dual-gauge rigs hold air or fluid inside the closed valve to detect any pressure drop. Every single valve passes through this pressure test before packaging, not a sample, the entire batch. Behind that simple brass fitting sits a far more demanding process for the valves running inside oil and gas systems. Industrial valve casting begins with simulation software modeling thermal behavior before any metal is poured. Wax patterns form the casting template, dipped repeatedly into ceramic slurry to build a shell, then melted out in hot water baths. The hollow shells sinter in furnaces before molten alloy fills them. Once cooled, castings are knocked free, ground smooth, shot blasted clean, and heat-treated to set their metallurgical structure. Dimensional inspection and surface testing follow before machining bores and critical faces to final tolerance. Internal gates, housing bolts, and hand wheels are assembled under controlled torque, and every finished valve is mounted on a hydrostatic rig to confirm sealing integrity before painting. Scale that casting operation across 3 factories and 2 continents, and the same fundamental steps repeat at industrial volume. A valve manufacturer running plants across China, Taiwan, and the Philippines operates a casting workshop producing roughly 1,000 tons of material monthly. Wax injection creates the baseline mold, followed by surface coating in structured layers on both faces before the shell goes through burning and casting. Molten metal poured directly into the prepared mold. Heat treatment then enhances strength and structural stability before mechanical processing brings each component toward final form. Vertical lathes and CNC tooling equipment handle the heavier cutting work. Quality control runs end-to-end. Incoming material inspection, physical and chemical testing, assembly verification, and final delivery checks. Once the rough casting exists, it still has to be cut to exact geometry. And at 450 millimeters of bore diameter, that cutting happens on a machine built for the load. A DN 450 ball valve body is mounted on the faceplate of a vertical lathe, with clamping fixtures and torque wrenches securing the casting dead center so it does not shift at speed. Before cutting begins, the technician sets parameters on the digital control panel and runs a trial rotation to confirm balance and stability. A dedicated turning tool then advances into the bore opening and outer face, removing excess metal in continuous passes. Thin ribbons of swarf peel away under friction heat as the surface finish closes in on the tolerance the bore requires for a tight ball-to-seat fit downstream. Push the bore size and pressure rating further, and the machining itself becomes the bottleneck of the entire valve supply chain. A 13-inch, 15,000-pound class-forged valve body begins on a CAD/CAM screen, where engineers verify the digital model and simulate every tool path before any cut runs on the real machine. Overhead cranes then position the oversized forging on the CNC table, where an automatic probe records the workpiece's exact starting coordinates. Heavy milling and turning passes follow at high cutting speed, with a continuous flood of coolant carrying away the metal chips that come off in volume. Specialized tooling reaches deep into the bore to face internal surfaces and grooves, clearing out the swarf that accumulates inside the cavity. The table rotates the block through multiple angles automatically, letting the same setup reach every face without manual repositioning. At the tooltip finishes the auxiliary threaded holes that close out the sequence on a body large enough that a setup error would mean remachining a forging worth far more than the time it took to cut. The scale of machining runs on equipment purpose-built for nothing smaller than industrial valve bodies. A large-sized boring and milling machine cycles through its multi-tool carousel, configuring the spindle head for heavy-duty cutting before the boring tool faces the exterior flanges of a large valve body. The cutting head then advances deep inside the cylindrical casing, where high-pressure coolant washes metal debris clear of the bore as the tool progresses. A technician monitors the cycle from a Siemens CNC control station while the machine continues its automated pass without manual intervention. When the operation moves to a different section of the workpiece, the entire column unit shifts along its axis track, repositioning the boring arm at the precise entry angle the next cut requires. A machine handling faces, bores, and angles that would otherwise demand multiple separate setups. Machining shapes the metal. What confirms it actually meets specification happens in a separate room entirely. After CNC milling and spherical turning bring the ball core to its initial finish, centrifugal grinding refines the roundness of the bore. Material verification follows immediately. Spectrometer analysis confirms steel grade and chemical composition, while a coordinate measuring machine scans the core's geometry against design tolerances. Impact testing on a pendulum rig checks the material's resistance to mechanical shock, paired with microscopic structural inspection and tensile testing on a universal testing machine. Surface roughness-hardness measurements follow on digital gauges. Finished components are laser-marked with material codes, including high-pressure alloys like Inconel 625, then verified once more by hand with calipers before shrink-wrapping and palletizing for dispatch. Every manufacturer builds a trunnion ball valve slightly differently, but the internal logic never changes, and taking one apart is the clearest way to see how it actually holds back pressure. A 3-inch, Class 600 trunnion-mounted ball valve separates first at the body adapter, unbolted and wedged open carefully to avoid damaging the ball inside. The adapter holds a seat ring backed by springs, an O-ring, and a fire-safe graphite seal, the layered components that maintain sealing even if the primary elastomer fails under heat. The trunnion itself, secured by 4 bolts at the base, supports the ball and lets it rotate. Removing it is the only way to free the ball from its stem slot. A separate mounting plate carries the actuator interface, while the stem bushing, fitted with its own primary and secondary O-rings, plus an anti-static device, controls rotation from above. Laid out fully, the valve resolves into body, ball, two seat assemblies, trunnion, stem, bushing, and mounting plate, each one repairable on its own, provided the seating surfaces have not been damaged beyond relapping. The seat ring that just came off that trunnion valve is only as good as the surface finish on its sealing face, and that finish gets restored by lapping, not by guessing. A dedicated lapping machine for ball valves up to 300 millimeters clamps both seat rings onto opposing chucks before centering the ball between them. A lapping compound brushed across the ball's surface carries abrasive particles into the contact zone as the machine drives both seats and ball through controlled multi-directional rotation under adjustable pressure. After the cycle, the ball emerges mirror-polished. A leak test with colored fluid confirms zero seepage once the seats are refitted. Surface roughness measurement on a digital profilometer puts numbers behind that visual result. Average roughness as low as 0.05 micrometers, with maximum profile height under 0.5 micrometers. Tolerances fine enough that the human eye alone could never certify them. Lapping restores a seat that is still salvageable. Most valves arriving for repair need more than that. They arrive locked solid. Stainless and carbon steel ball valves from 2 to 12 inches in 150 and 300-pound pressure classes get sent in for the same recurring failure, product buildup inside the body that freezes the ball in place. The repair sequence starts with full disassembly. Sandblasting the exterior while solvent and wire brushing clean the interior without abrading critical surfaces. Manufacturer-specified seat kits, available in virgin or reinforced Teflon, seat into a groove inside the body, with the ball rotating directly against both seats once reassembled. A body gasket contains pressure across the joint, while stem packing and a thrust washer prevent leakage past the rotating shaft. Reassembled valves go to a test stand for hydrostatic testing at 225 psi on each side independently, with zero leakage required on both. A wire tag recording size, material, job number, date, and manufacturer closes out the repair before the valve ships back into service. At DN 1400, repair tooling and lapping machines no longer apply. Getting a valve this size assembled at all requires overhead cranes doing work that hands cannot. Two halves of a welded ball valve body, along with the ball core itself, sit pre-positioned on the shop floor before assembly begins. A crane-mounted support frame lowers a large internal seal ring into one body half, where workers manually align the threaded mounting holes and apply lubricant along the internal locating surfaces. The second body half then gets lifted clear by overhead chain hoist, repositioned to open ground and rigged at its load-bearing points, so the crane can rotate it a full 180 degrees, flipping it from its resting orientation to the position needed for final mating. Once inverted, the crane raises this second half and guides it precisely toward the ball core waiting at the center of assembly. The body lowers slowly, enclosing the ball completely and seating against the first half below. Workers then check concentricity between the two halves by hand, confirming the joint sits true before the structure is considered complete. At this scale, every step that a smaller valve handles with a bench vise and a wrench instead runs through rigging calculations and crane choreography. The same fundamental ball and seat principle as the brass valve that opened this story, scaled up by a factor that changes the entire assembly method. Manufacturing and repair both end the same way, getting the finished valve into the ground on a pipeline that cannot fail. A 108-inch gate valve, the largest of its kind built, gets lowered by heavy crane into a reinforced concrete vault on the Integrated Pipeline Project, connecting East Texas reservoirs to the Dallas-Fort Worth area. Workers in the vault use guide ropes to align the valve body precisely with the waiting pipe connections as it descends, then verify clearance with measuring tools before the gate, a square mesh wedge, goes in separately. The upper bonnet follows by crane, rotated into position over the body's waiting bolt circle. Hydraulic torque equipment tightens the bonnet bolts to specification, and the gate lowers into its seated test position, completing one of 6 identical valves the project requires, each standing 44 feet tall and weighing 108 tons once assembled. But controlling flow only matters if something generates that flow in the first place. A pump manufacturing and service center west of Paris, running on more than a century of operating history in France, opens its process with engineers presenting pressure system drawings on screen and developing tailored solutions in 3D CAD before any metal moves. The 8,300 square meter facility runs CNC lathes and milling machines, shaping pump components, with technicians cross-checking dimensions against drawings using calipers and measurement gauges at every stage. Large rotating shaft equipment runs automated machining in enclosed bays. Once components are ready, laser scanning builds a 3D model of impeller surfaces for inspection, while mechanical dial gauges check balance and runout on rotating parts. Heat guns warm fitted components before pump stages are pressed vertically onto the main shaft, and the assembled rotor goes onto a support stand for concentricity verification. Maintenance work on rotating equipment in for service follows a parallel track, cleaning, scraping corrosion, and recalibrating housing components and bolts. Finished assemblies move by crane into module positions before the complete pump connects to a large-scale test bed, simulating the most extreme operating conditions the unit will face in service. On screen throughout the test run, the final checkpoint before a pump engineered on a drawing becomes one trusted to run continuously in the field. A pump buried hundreds of meters below ground cannot be repaired easily once installed. That is why a submersible pump must be built as a completely sealed motion system before it ever enters a well. Production starts with raw material inspection, followed by machining cast and stamped parts on lathes, drilling machines, and milling equipment. Pump housings, impellers, shafts, and bearing seats are cut to precise dimensions so rotating components remain aligned during operation. Motor stators are wound with copper wire and insulated before being installed inside sealed housings that separate electrical parts from groundwater and process fluids. Assembly proceeds stage by stage. Impellers are mounted along a central shaft, while bearings and bushings are fitted between sections to manage radial and thrust loads generated during rotation. Mechanical seals and sealing rings are installed at key locations because even a small leak can damage the motor. The completed housing is tightened under controlled torque and subjected to functional and pressure testing. Only after confirming sealing integrity, smooth operation, and performance does the finished submersible pump move to packaging and shipment. Step back from the submersible pump sealed isolation, and the broader centrifugal pump category covers an enormous range of industrial duty. A manufacturer with origins as a small iron foundry in Austria has built more than a century of experience designing centrifugal pumps for freshwater, seawater, and wastewater systems, covering irrigation, flood control, offshore platforms, desalination plants, cooling water circuits at power stations, and mine dewatering. The same pumps sometimes run in reverse, as small turbines, generating power rather than consuming it. Development and testing now run across 8 locations, spanning Austria, Canada, China, Germany, Finland, and Switzerland, with research centers networked together to share engineering knowledge across the group. Every workshop continuously evaluates its own manufacturing process to shorten lead times while holding quality and reliability standards, with quality assurance requirements defined uniformly and implemented the same way at every production site worldwide. Consistency that matters because a pump shipped to a desalination plant faces entirely different fluid chemistry than one destined for a paper mill. Centrifugal pumps cover a vast range of services, and at the top end of that range sit vertical pumps built specifically to move enormous volumes of water for power generation. The 7.1 APM vertical circulating water pump, assembled for one of the largest supercritical power plants in Southeast Asia, carries a column 2.7 meters in diameter and stands 21.5 meters long. Rated for flows up to 66,000 cubic meters per hour, it can fill an Olympic-sized swimming pool in under 3 minutes at full output. Assembly begins with the outer column and suction bell, followed by structural installation into position. The pumping element and diffuser bearing are built up separately before the completed assembly drops into place inside the column, where a shaft coupling establishes the main mechanical connection. The inner column and foundation plate follow, then the discharge head, maneuvered into position by crane and lowered to mate with the assembly below. A stuffing box and bearing housing complete the rotating shaft seal, with a motor support frame installed before the drive motor itself is lifted into its final position at the top. The finished pump connects to the facility's expanded test loop, capable of testing flows up to 90,000 cubic meters per hour, one of the largest and most versatile open test benches anywhere, where the assembly runs through full operational testing before it ships to the power plant it was built to serve. Move from clean circulating water to whatever a mine or dredging site actually produces, and the pump itself has to change category entirely. A slurry pump and dredging equipment manufacturer builds both electric and hydraulically driven submersible units designed to handle solid concentrations up to 70% by weight, fluid that would destroy a standard centrifugal pump within hours. Electric slurry pumps lower directly into settling ponds or waste containment areas, where an agitator at the base breaks up settled solids before they enter the pump chamber. Hydraulic slurry pumps connect to excavators or independent power packs, with the hydraulic arm guiding the pump precisely to the working depth, while cutter heads break apart compacted clay or dense sand simultaneously with pumping. Remote-controlled dredge vessels extend the same principle further. Compact units anchored in tailings ponds or reservoirs, operated by secure radio control from shore, following a preset route while continuously dredging accumulated sediment from the bottom. Across mining sites, refineries, and port construction projects, these units run continuously in environments abrasive enough to wear through standard equipment quickly. The entire design philosophy built around handling the densest solid mixtures directly, rather than filtering them out before pumping. That same concrete pumping principle, built into a mobile truck-mounted unit, comes off an assembly line that runs almost entirely without human hands. Production begins with unmanned blanking, where automated cranes position steel plates for laser cutting. Robotic arms sort the cut parts before welding robots assemble major frame sections with high-precision welds. Unmanned CNC machining centers then mill and bore structural components without direct operator handling. Parts continue through an enclosed intelligent paint shop, moving automatically on overhead conveyors. An automated storage and retrieval system manages inventory and supplies components to the assembly line. Large boom assemblies are lifted onto truck chassis by cranes, while technicians verify alignment and bolt torque. Completed units enter a testing yard where outriggers and full boom systems are deployed before delivery. Hydraulic drive shows up far outside industrial pumping too, anywhere multiple mechanical motions need independent control from a power source. A pumpkin seed harvester uses separate hydraulic circuits for its pickup drum, crushing unit, screening drum, and unloading auger, all controlled from the cab without mechanical linkages. Long before electric submersible pumps and hydraulic slurry units, entire cities depended on steam to move water uphill. Built in 1914 to supply the Staffordshire potteries, a preserved pumping station runs horizontal compound tandem engines, high and low pressure cylinders in sequence, driving a flywheel for momentum. Coal feeds automatically from hoppers through a screw mechanism into the boiler firebox, with hot flue gases circulating the full length of the boiler before heating its underside on the return pass. The high-pressure pumps moved water 5 miles uphill to a reservoir 350 feet higher, capable of 3 million gallons daily, a scale of lift that modern submersible pumps achieve with a fraction of the machinery and none of the coal. Pumps in a refinery do not run unattended. Someone has to control the pressure and flow they create continuously around the clock. Petroleum pump system operators run the equipment processing and refining crude oil, testing it and feeding it into pipelines as the first stage of distribution. Gas plant operators control compressors along pipelines to maintain the specified pressures utility companies depend on. Gas compressor and pumping station operators transmit and pressurize gases, including butane, nitrogen, and hydrogen, through the same category of rotating equipment. Work environments range from temperature-controlled control rooms to cold outdoor facilities and hot, noisy plants, requiring protective gear through most of a shift that frequently runs longer than 40 hours. The physical demands are constant, and staying alert through fatigue matters as much as the technical training behind the role. South Africa applies pumped storage technology on a scale large enough to move an entire mountain's worth of water every day, using reversible pump turbines to balance the national power grid. The Ingula pumped storage scheme links an upper and lower dam, each holding roughly 22 million cubic meters of water, through more than 9 kilometers of tunnels connecting to an underground turbine hall 140 meters long. 4 reversible pump turbines, each rated at 333 megawatts, generate electricity during peak demand by releasing water downhill through the system, then reverse to pump that same water back uphill during low demand periods overnight and on weekends. The 470-meter elevation difference between dams pushes water through pressure tunnels lined with high-strength, quenched and tempered steel, engineered to withstand internal pressures up to 72 bars. A dedicated on-site manufacturing facility fabricated the steel tunnel linings locally, rather than transporting finished sections over mountain roads, importing 177,000 tons of steel and rolling, welding, and pressure testing each section before installation. The completed scheme functions as a mechanical battery for the grid. Water pumped uphill during quiet hours becomes stored energy released the moment peak demand strikes, the entire system existing because reversible pumps can move that much volume against that much head repeatedly for decades. Pumps build pressure. They move nothing. Every push, lift, and clamp in heavy industry happens at the cylinder, where that pressure finally becomes directional force. At a Norwegian facility north of Trondheim, hydraulic cylinder and accumulator production has continued since 1956 in a plant founded back in 1936. The scale of what gets built there is unusual. Piston diameters span 20 to 2,000 millimeters. Stroke lengths reach 20 meters. Each unit is engineered for harsh climate operations where a failure underwater, offshore, or in Arctic conditions is not recoverable. A multitasking CNC machine combines turning and milling in a setup, cutting the accumulated error that comes from transferring a long shaft between separate machines. Submerged arc welding with custom joint geometry handles the welds on large tubes, controlled by certified welders working to customer and class society standards. Heat pumps, drawing thermal energy from the sea outside the plant, power the entire production environment. Before any cylinder leaves, it passes pressure testing, function testing, cleanliness control, and particle counting against whatever standard the application demands. A dedicated life cycle department repairs and services every cylinder, accumulator, and damper the plant has shipped. A cylinder operating 20 years at sea will eventually need rebuilding, and rebuilding it correctly matters more than building a new one. A 22-meter stroke at 700 bar working pressure depends on bore finish, seal geometry, and rod metallurgy measured in microns. Any drift in those numbers, and the cylinder either leaks or seizes. LVIB production line handles 700 bar operating pressure, rod diameters from 6 to 500 millimeters, piston diameters from 20 to 800 millimeters, and strokes up to 8,000 millimeters, with partner facilities extending to 22,000 millimeter strokes for the largest applications. Engineers model every internal dimension in CAD before metal moves. Bandsaws cut billets to length under coolant, then CNC turning and boring open the board to spec under continuous flood. Seals are cut on a dedicated station and checked with calipers before assembly. Piston rods, already fitted with their seal rings, slide into the bore on a powered carriage and get capped by the gland under a rubber mallet, then torqued down with a pneumatic gun. Hydraulic lines connect at the test ports. The rod cycles to confirm the seals hold, and a laser etches the model number, serial, and date onto the steel before paint. Inside a steel mill, hydraulic cylinders don't have the option of failing. A jammed mud gun cylinder during a tap-out, a stuck cylinder on a continuous casting machine, a failed cylinder on a hot strip mill. Each one halts a chain that runs at thousands of dollars per minute. Steel mill cylinders cover the entire production chain. Iron-making machines, mud gun sealing blast furnace tap holes, torpedo cars moving molten metal between stages, electric arc furnaces, blast furnaces themselves, continuous casting machines, hot strip mills, plate mills, rolling mills, automatic gauge control systems, and billet mills all run on hydraulic actuation. Each of those applications places different demands on the cylinder. Mud gun cylinders work in radiant heat near molten iron. Continuous casting cylinders work in constant vibration and steam. Rolling mill cylinders work under massive cyclic load thousands of times per shift. Plate mill and billet mill cylinders work under shock loads from material entering the rolls. AGC cylinders work in closed-loop position control where micron-level response matters more than raw force. What ties the catalog together is heavy industrial cylinder work, large bores, thick-walled barrels, rods plated to resist abrasion and corrosion, seals selected for temperature and contamination, and end caps designed to survive being struck. A cylinder that runs 10 years inside a steel mill has earned its place and built the case for everything else hydraulic in heavy industry. Crushing rock is a contest between the hardness of the stone and the geometry of the chamber pressing on it. Multi-cylinder hydraulic cone crushers win that contest by adjusting the chamber in real time, something fixed spring crushers cannot do. Feed material drops into a hopper, runs up a series of conveyors traversing the quarry's sloped terrain, and lands inside the cone crusher feed bowl. The crushing head spins eccentrically inside the bowl, squeezing rock between the mantle and the concave liner until fragments are small enough to pass through the discharge port at the bottom. Hydraulic cylinders ring the crusher body. Their job is to control the gap between the mantle and the concave, the closed-side setting that determines product size. Pressing them down tightens the chamber and produces finer material. Releasing them widens the gap. When a tramp piece of uncrushable steel enters the chamber, the same cylinders relieve pressure instantly to let it pass without damaging the crusher. The hydraulic system also clears the chamber after a power loss, instead of leaving the crusher locked under load. Discharged product runs out below to a conveyor and onto a vibrating screen for grading. A flat sheet of stainless steel becomes a deep-bowled cooking pan in about 4 hits of a hydraulic press. A long strip of 304 stainless feeds into the first press, which blanks circular discs and drops them into a tray. Each disc moves to the deep draw press, where the ram descends and pushes the metal into a deep cavity die to form the pan body. A third station punches and trims the rim flange. A heavy tonnage vertical press refines the base radius and stiffens the bottom. The final station rests the pan upside down and shears the excess metal cleanly off. A small hydraulic press table can produce more shaped iron in a shift than a traditional blacksmith does in a month without heating anything. The hydraulic wrought iron table uses interchangeable die sets to twist, scroll, emboss, hammer, and press cold steel bar stock. With one die, the press shapes belly picket profiles in 4 configurations and produces 875 textured and pressed pickets in a single day. A V-block die with a round mandrel takes a pre-twisted bar and cold bends 2 90-degree corners into a clean handle. Another die incrementally bumps a heavy flat bar into a smooth gate arch. A scroll correction die nudges loose scrolls into exact alignment with the paper template laid on the table. Loading a 30-foot boat onto a yard trailer used to take 3 people and 20 minutes. With a hydraulic boat trailer running fully articulating cylinders, 1 operator and a wireless remote do it in less than 5. 2 trailer sizes cover the working range, a 10,000-pound model handling boats from 18 to about 33 feet, and a 20,000-pound model for larger hulls. The hydraulics articulate left and right independently. The tongue is hydraulically adjustable, and either side of the trailer can be raised or dropped to match the angle of a boat sitting crooked on its stands. Rear bunks slide up and down. Center bunks come in 2 sizes and adjust to the hull. A hydraulic cylinder on the tongue drops the entire center of the trailer toward the ground, which means lower clearance for loading off blocks or forks than a fixed frame design allows. Wireless or manual operation. DOT-approved running lights, tail lights, and brake lights for road travel. Tie down D-rings on the center and bottom of the frame for highway transport. A 16-ton empty trailer turns into a 30-ton loaded outdoor stage in under 20 minutes, using hydraulic outriggers, hydraulic floor wings, and a hydraulic LED screen lift, all driven by remote. The ST-130 hydraulic stage trailer measures 13 meters long, carries up to 30,000 kilograms of load, and folds out into a stage area extendable to 160 square meters. Outriggers level the rig, cylinders lift the roof wings, and lower the deck panels symmetrically on both sides. A 30-ton excavator parked on a near-vertical mountain face has no business holding a drilling rig, unless the rig clips onto the excavator's existing hydraulic circuit and weighs almost nothing on the boom. The MRA-line hydraulic drilling mast attachments do exactly that. Each unit bolts onto the end of an excavator's stick or onto a telehandler boom, taps into the carrier machine's hydraulic supply, and turns that carrier into a mobile drilling rig with no separate power pack. The mast rotates 360 degrees on its mount, so the operator can flip between horizontal drilling into a rock face and vertical drilling into the ground without repositioning the carrier. On a standard tracked excavator, the attachment works against quarry walls, road-cut benches, and slope stabilization holes. Mounted on a spider excavator with 4 independent stabilizing legs, it reaches near vertical cliff faces and forested slopes where conventional tracked carriers cannot stand. On a telehandler, the operator drives the mast directly into a rock face from a stable cabin position, watching the drilling angle on a digital display. More than 600 units of the MRA line have shipped across 14 different model variants, all running on the same principle: borrow the carrier's hydraulic pressure, channel it through the mast's actuators, and convert a general-purpose construction machine into a purpose-built drilling platform on demand. Excavator hydraulics don't have to end at the bucket. Plug a hydraulic magnet onto the hammer line. The same pressure that swings the boom now generates an electromagnetic field strong enough to lift 11 tons of plate steel. The HMG 1150 magnet runs off the excavator's existing hammer line hydraulics. No additional installation, plug and play. Maximum lifting capacity reaches 11,000 kilograms on a clean, flat steel plate, or 650 kilograms on loose scrap. On a working demolition site, the magnet sweeps the rubble, picks reinforcement bars and structural offcuts out of broken concrete, lifts long lengths of rebar trapped under collapsed slab pieces, and drops each load onto a separate scrap pile for recycling. The carrier excavator never needs an auxiliary generator to make it work. Every cylinder, hydraulic or combustion, lives or dies by the surface of its bore. The cleanest place to see that bore being born is inside an aluminum die casting line. Ingots stack into a melting furnace and convert to liquid. The molten aluminum is stirred and skimmed for impurities, then transferred to a high-pressure die casting machine that injects it into a mold. A robotic arm pulls the raw block out, trims flash, and sends it onward to CNC machining and assembly. Hydraulic cylinders push and pull in straight lines. The other half of heavy industry has to spin, and the heavier the load on a spinning shaft, the more dangerous friction becomes. That's where bearings start to matter more than the engines they support. Big-size spherical roller bearings handle the worst of it. A representative unit measures 1,320 millimeters bore, 1,850 millimeters outside diameter, 530 millimeters wide, and weighs 4,420 kilograms. Its dynamic load rating reaches 23,200 kilonewtons. Static load rating, 63,500 kilonewtons. Manufacturing starts at the forge. A heated steel billet, upset pressed to spread, pierced through the center, and ring-rolled to final ring diameter. Vertical lathes turn the bore, faces, and outside diameter, then cut the curved raceway. Cages get drilled with roller pockets. Roller stock is sawed, turned to barrel profile, and heat-treated. Rings are quench-hardened, then ground to micron tolerance on raceways and surfaces. Final assembly places rollers into cages, drops the assembly inside the outer ring, and snaps the inner ring into position with leverage. Steel balls inside bearings deviate from perfect roundness by less than 1/10 of a micron. A human hair is 300 times rougher. Industrial steel ball production runs through 7 stages. Wire arrives in coils, gets cut into short cylindrical sections, and presses together into a blank with 2 visible features, a Saturn ring around the equator and a pole. Flashing removes both, leaving a roughly spherical blank. The blanks pass through repeated grinding stages that round them out evenly. Hardening in a furnace gives the steel the durability to survive bearing pressure. Annealing and quenching refine the structure. Finish lapping, high-precision grinding between charged plates brings the balls to final tolerance. Washing happens repeatedly between every stage to remove embedded grit that would otherwise destroy the next surface. Measurement happens under microscope in dedicated rooms, checking roundness and roughness on each finished ball before packing. Larger plants ship millions of finished balls per day into wheel bearings, transmission bearings, and pump bearings worldwide. A factory making 3 million spherical roller bearings a year cannot afford to grind one bearing twice, which is why heat-treated parts arrive ready and every grinding pass is final. A spherical roller bearing factory operating since 1911 produces roughly 3 million units annually. Heat-treated rings arrive from suppliers worldwide. Inner and outer rings move through ring face grinding first to set thickness and squareness, then to outside diameter and bore grinding, then to raceway grinding and honing, the critical surfaces finished to within microns. A washing and drying line strips away abrasive residue. Operators hand-assemble rollers, guide rings, and cages into each bearing. Laser engraves the bearing designation onto the ring face. For sealed variants, grease pumps in automatically and seals press into the bearing housing. Every bearing undergoes manual inspection before corrosion prevention oil treatment and automatic packing. The full output ships to industries running heavy loads, shock loads, and shaft misalignment in equal measure. Tapered roller bearings carry both radial and axial load on the same set of rollers. The inner ring tolerance that makes that work is so tight that the line cannot tolerate a defective part reaching the next station. A tapered roller bearing line in Zaragoza machines the inner ring raceway first, then a spider arm inspection unit checks the ground dimensions and rejects any out-of-tolerance ring before it reaches flange machining. Inner diameter is ground with in-process control because the tolerance window is too narrow for end-of-line inspection alone. Temperature is measured continuously to compensate dimensional drift caused by thermal expansion. Inner diameter, conicity, and bore ovality get 100% checked. Adjustments feed back automatically to the grinder. Final cone assembly height is checked on every unit by robotic gauging. Every miniature ball bearing in a dental drill, a hard drive spindle, or a precision instrument went through the same 5-step automatic dance, and a human hand never touched it. Miniature bearing assembly runs entirely on automated stations. Rings load into a vibratory feeder that orients each one and sends them down the line. An automatic gauge measures each outer ring. A second gauge checks each inner. Mismatched rings get rejected. Balls flow through a brass tube sorter that selects only those within size tolerance. Inner and outer rings come together on a common axis. The balls drop into the annular gap. Spacers press in to distribute the balls evenly around the ring. The cage drops into place and is riveted shut, locking the assembly together as a finished bearing. A finished bearing that sounds rough on a vibration tester gets rejected, no matter how clean it looks under the microscope. Inner and outer diameter gauges check every ring at the start of an automotive ball bearing line. Cleaning, sorting, and matching paired rings before cage installation and riveting. Optical defect detection scans the balls and cage. Clearance and flexibility testers spin each bearing under load. A bearing vibration tester records the acoustic signature and rejects noisy units. The line grease fills both sides, presses sealed shields into place, and spins the bearing at high speed to distribute the grease evenly before final visual inspection. Different bearing types are not interchangeable, and an industrial bearing plant typically produces 10 to 20 distinct product families for 10 to 20 distinct customer industries. A large bearing manufacturing hub in Vadodara runs 2 production plants on custom German-built precision machines. One plant produces spherical roller bearings, cylindrical roller bearings, tapered roller bearings, and wheel set bearings, the latter critical to railway rolling stock. The second plant handles heat treatment, grinding, honing, and assembly of deep groove ball bearings and large-sized bearings used in critical applications. Both plants run quality checks at multiple production points to match standards held in the German reference factories. Forcing a 1,300 mm spherical roller bearing onto a shaft cold is how rings crack. Heating it to the right temperature is how shafts last 20 years instead of 2. Spherical roller bearings with cylindrical bores rely on heat for mounting because their interference fits run tighter than other bearing types. An induction heater raises the bearing temperature without exceeding 110 degrees Celsius. Anything above that risks damaging the steel structure. Protective gloves are required. The bearing is held against the housing shoulder until it cools enough to grip the shaft on its own. Dismounting uses a combination technique. The shaft is prepared with oil injection passageways. A high-pressure pump injects oil between the bearing bore and the shaft, while a jaw puller draws the bearing off. The internal radial clearance, designated C3 or C4, must be matched on any replacement bearing to keep the assembly within its original load profile. A slewing ring is the single component that lets a 200-ton excavator upper structure rotate freely on its undercarriage, lets a tower crane swing a load through 360 degrees, and lets a wind turbine yaw to face the wind. When it wears out, the entire machine stops, and the repair itself is a precision job most people never see. Custom slewing bearings range in outside diameter from 100 mm up to 6,000 mm. Repairing them instead of replacing them saves the customer the cost of new manufacture. The teardown begins at the workbench. A technician removes the cover plug at the side of the ring to access the rolling elements. A long, slide hammer-style puller goes in through the access port and walks each ball and spacer out of the raceway one by one until that section of the ring is empty. The rubber seal ring around the perimeter comes off next, releasing the mechanical link between the inner and outer ring. The whole assembly sits on a circular turning stand. Slings clip into the existing bolt holes on the inner ring. An overhead crane lifts the inner ring straight up, slowly, until it clears the outer ring entirely, exposing the grease-packed raceway and dropping any remaining loose rollers into a tray below for inspection and replacement. Five-axis CNC machining does more than remove metal. It reaches surfaces a three-axis machine cannot touch without refixturing. Large gears, gearbox housings, and bearing components now get machined this way for exactly that reason. HFC milling, high-feed cutting, runs the cutter at very high feed rates with shallow depth of cut, distributing the load across many teeth and protecting the tool while pushing material removal rate well above conventional milling. The technique earns its place on hard mold steel and contoured surfaces, where a conventional ball end mill would chatter, burn out, or take 10 times longer. A five-axis machine clamps the workpiece once and reaches every face by rotating the table and tilting the head, instead of stopping to reclamp the part for each new surface. Setup begins with virtual machine simulation that runs the toolpaths through a digital twin of the real cell before any cutter touches metal. Collisions, gouges, and overtravel get caught in software rather than in scrap. A library system pulls the correct tools from a digital catalog, with one recent addition being an indexable insert barrel cutter that holds carbide inserts on a curved shank to finish contoured surfaces faster than a solid ball end mill. Roughing first, semi-finishing next, then five-axis HFC finishing closes the part out to drawing tolerance for the water jacket mold it was always designed to become. Gear teeth get all the attention. The housing that holds them in alignment under torque gets almost none. Yet a gearbox with perfect gears inside a misaligned housing wears those gears out in months. A gearbox housing for an industrial drive is a large cast or fabricated steel block with multiple parallel bores that must hold concentric to within tens of microns over distances of half a meter or more. The job runs on a horizontal machining center, a CNC platform with a rotary table that swings the workpiece on its axis, presenting different faces of the housing to a spindle without reclamping. A long boring bar enters the bore at low rotation, increasing speed as the cut steadies. Coolant floods the cutting zone. The table rotates to bring the next face into position. Each bore comes out concentric to the others because the entire housing was machined in a setup, not in stages on multiple machines. A large industrial gear weighing several tons can have every tooth profile measured to within 2 microns, finer than the diameter of a human red blood cell. That's not vanity precision. It's what separates a gearbox that runs 10 years from one that fails in 18 months. Large industrial gears are machined in plants equipped for the weight as much as the precision. An overhead crane rated for 75 tons handles raw forgings and finished gears as they move between stations. 3 operations dominate the floor: gashing, hobbing, and gear cutting. Gashing roughs out the spaces between teeth in a heavy first cut, removing the bulk of material before any finishing tool sees the workpiece. Hobbing follows. A hob is a worm-shaped cutter with cutting edges arranged in a helical pattern. It rotates against the gear blank in a precisely coordinated motion that generates each tooth flank in continuous chips rather than carving one tooth at a time. Coolant floods the cutting zone throughout, removing heat that would otherwise distort the gear and shorten tool life. Final measurement runs on a coordinate measuring machine inside a temperature-controlled inspection room. Probes sweep each tooth flank and compare actual geometry to the design model. Deviations under 2 microns pass. Anything larger goes back to the finishing station before the gear is allowed to ship. Gears mesh. Bearings spin a shaft. Neither carries motion more than a few centimeters on its own. Chains take that same rotation and walk it across a factory floor, up a mine ramp, or down the length of a cement plant conveyor. Inside a roller chain factory, production begins with high-quality domestic wire and strip steel selected for consistent material properties and faster response to customer requirements. Every die, punch, and forming tool is designed, manufactured, and maintained in-house, allowing tighter control over accuracy and production schedules. The facility's largest stamping press operates at 500 tons, producing the heavy bars used to form link plates for larger chains. Its high tonnage allows multiple progressive stamping operations to run in sequence on a single machine, increasing productivity. Bushings, which connect links and create pivot points, are formed on dedicated equipment. A rounded edge is pre-shaped into the strip steel to prevent damage during assembly. Heat treatment modifies the steel's molecular structure, creating chain components that combine strength with the ductility needed to absorb shock loads. Because chains work under tension rather than compression, durability at every pivot point is critical. Shot peening strengthens surfaces with steel ball impacts, while ball sizing forces a hardened carbide ball through side plate holes to reinforce the pitch holes. 5 components are assembled automatically into continuous chain lengths, pre-stretched, then immersed in 230 degrees grease for 20 minutes before final handling. 60 countries, 8 factories, 2,000 employees, and no length of finished chain leaves the building until the test bench confirms it can survive 10 years inside a sugar mill or a cement plant. Steel coils arrive at the rolling shop and feed into mechanical presses that punch each link plate and shear it to dimension. Heat treatment uses a multi-purpose furnace and a controlled atmosphere mesh belt furnace to harden the components. Then shot peening relieves surface stress. Quality control follows immediately. Hardness gets checked on dedicated testers. Metallographic analysis under digital microscope verifies the grain structure of the heat-treated steel. Assembly combines link plates, pins, bushings, rollers, and side plates into continuous chain on a hybrid manual and automatic line. 3 tests then run on each finished chain. Braking load pulls every length to its rated tensile capacity. Length measurement verifies pitch accuracy. Fatigue testing cycles each chain at load to confirm it can survive the millions of flex cycles a real installation imposes. The chain then oil dips to displace moisture before storage and shipment. Standard chain fails the moment it meets food-grade contamination rules, saltwater corrosion, or environments where lubricants simply cannot exist. That is the reason a specialty roller chain plant in Massachusetts produces stainless steel chain, multi-strand chain, lube-free chain, corrosion-resistant chain, and made-to-order chain alongside its standard ANSI line. Material certifications, in-process controls, component checks, vision systems, and final inspection follow every chain through production. The lube-free variant uses sintered bushings and patented lube groove geometry to run without external grease. Each component starts in select alloys, gets heat-treated, then receives post-process finishing for peak strength and durability. Belt and chain conveyors move material along a line. Screw conveyors move it along a spiral. And that spiral itself is a flat steel disc stretched into a helix by brute mechanical force, one weld at a time. Construction begins with circular steel discs cut from sheet stock. An oxy-gas torch traces an inner circle on each disc to create the shaft hole, and the center slug is removed. The discs stack onto a long shaft. A welder tack welds the cut edges of adjacent discs together, then a chain hoist hooked to one end of the disc stack pulls hard along the shaft, stretching the welded discs into the helical flight that defines a screw conveyor. Each roller in a mining conveyor spins for tens of thousands of hours under tons of ore before it is replaced. Producing rollers at the volume mining requires means moving the line from 250 a shift to over 1,000 a shift without breaking quality. A specialist conveyor roller plant in Australia has spent 15 years serving mining clients, where reliability and total cost of ownership outweigh nearly every other purchasing criterion. Project orders run from a few hundred rollers up to past 50,000 on a single contract. 2 major contracts, each completed using composite materials developed in-house, delivered performance metrics above customer expectations. Scaling production capacity matters because a single mine site can demand replacement rollers in lot sizes that would shut down a smaller shop, and downtime on a primary ore conveyor is measured in millions of dollars per hour. Conveyors don't only carry material. Place the right device above the belt, and the same conveyor becomes a sorting line, pulling ferrous waste out of the stream before it damages the equipment downstream. A magnetic separator on a conveyor belt removes iron and steel pieces from mixed material, coal, or recycled aggregate, food product that would otherwise reach the next crusher, mill, or screen. 2 main installation patterns exist. The suspended type hangs perpendicular to the belt at the discharge end, lifting tramped metal up and dropping it sideways into a separate chute as the conveyor passes underneath. The head pulley type replaces the conveyor's discharge pulley with a magnetic pulley, holding ferrous material to the belt while non-magnetic product falls free, and releasing the captured metal once it leaves the magnetic field. Permanent magnets cover most applications. Electromagnets handle the heaviest loads. Manually loading scrap tires into a baler is slow, back-breaking work, and the throughput cap of an entire recycling yard usually traces back to that one bottleneck. Stack an inclined conveyor between the tire pile and 2 balers, and the bottleneck disappears. The inclined tire baler conveyor lifts loose tires from ground-level loading into the hopper of a dual baler arrangement. The hopper holds up to 600 tires at once. Loose tires can be tipped in from a van, an excavator bucket, or a tipped container. Modular sides on the conveyor adapt to whichever loading method the site uses. The conveyor delivers tires directly to operator hand height on an elevated platform between 2 Mk2 balers. One baler compresses and ties off a finished bale while the operator loads the second. The cycle never stops. Throughput rises while the operator stops bending toward the ground. Conveyors carry. Some also flip. A modular mesh conveyor fitted with a pneumatic rotation mechanism turns each passing box through 180 degrees before sending it onward to a pelletizing robot. As a box enters the station, a sensor triggers an L-shaped guide plate. Pneumatic cylinders pivot the box on its axis, while the belt holds it in place. Then the plate retracts and the rotated box continues to the next station. Orientation corrected, robot pickup simplified. Atacama Desert Mining produces ore by the kiloton every hour. Trucking crushed copper from underground bins to surface processing would mean hundreds of round trips a day. The most powerful belt conveyor system on Earth eliminates the trucks entirely. The Chuquicamata underground mine project moves crushed copper from underground storage bins to the surface and onto the processing site through a 13-kilometer conveyor system. Roughly 7 kilometers of that distance runs underground, climbing 900 meters of vertical elevation along the way. Total installed drive power across the system reaches 58 megawatts, distributed across 11 gearless synchronous motors of 5 megawatts each. The underground conveyors carry 20,000 kilowatts of drive power per belt, working in concert with the first commercial deployment of the ST-10000 steel cord belt, the strongest conveyor belt ever produced. Design capacity reaches 11,000 tons per hour. The 6-kilometer surface conveyor adds another 287 meters of elevation and carries horizontal curves across 60% of its length, with bridges supporting more than half. Gearless drive technology has cut carbon dioxide emissions by 66% versus the trucking alternative. Every motion system covered so far, every cylinder, bearing, chain, roller, only earns its place after testing. Heavy industry doesn't trust feel, it trusts the load test. And the larger the system, the heavier the test load has to be. On the second Ford-class aircraft carrier, that test load takes the shape of 12 bright orange wheeled sleds, 6 different weights up to 80,000 pounds apiece, each one engineered to simulate a real aircraft. The system being proved out is the Electromagnetic Aircraft Launch System, known as EMALS, which replaces the steam catapults of every previous U.S. carrier. Following successful no-load testing on the 2 bow catapults, dead-load testing then began. The sleds get launched off the carrier's bow into the James River at varying speeds and weights, simulating everything from the lightest unloaded trainer to a fully fueled and armed combat aircraft on a maximum weight launch. Once each sled hits the water, it gets retrieved and relaunched. The cycle repeats until the catapults have proven they can handle every weight class of fixed-wing aircraft in the carrier air wing. Electrical checks, close tolerance alignments, piping work, structural builds, none of it actually proves anything until the button is pushed and the sled leaves the deck at flying speed. Lessons learned on the previous carrier are folded into the build and testing of the next 2 ships in the class. Hoisting heavy cargo with one strap puts shear and bending stress on whatever is being lifted. Spreader beams distribute the load to prevent that. And proving the beam can survive what it will eventually carry in service means hanging 2,420 tons from it on a test rig. 2 Modulift spreader beams executed the test at a port facility in Dubai. The rigging combined 110-ton and 50-ton water bags, cable-laid grommets, and round slings sourced from specialist equipment suppliers around the world. The setup ran in stages. Heavy crane hooks first lowered onto the spreader beams, which were laid out across the quayside between the cargo handling area and the water. Crews shackled the orange water bags onto the rigging through high-capacity cable-laid grommets. The crane raised the entire assembly clear of the ground and swung it out over open water for safety clearance, and held the suspended load at the verified test weight for the dwell time required by the certification protocol. What this proves is twofold. First, the beam itself survives an overload condition without buckling or deforming. Second, every component in the rigging chain, shackle, grommet, sling, water bag, performs as rated. Once the dwell completes, the bags discharge their water directly into the sea and the rig dismantles. The certification carries forward to every real lift afterward. Air winches lift loads with compressed air rather than electricity, which makes them legal in explosive atmospheres, on oil rigs, on offshore platforms, and anywhere electrical sparking is a fire hazard. The trade-off is mandatory inspection testing before first service and retesting every year afterward. Each air winch undergoes a full functional inspection before it leaves the test bay. The compressed air supply line connects to the inlet. The winch runs through its full speed range under no load to verify smooth operation, brake engagement, and clutch function. Rated load gets applied through a calibrated test weight, or hydraulic load cell, held for a defined dwell, then released to verify the brake holds. An overload test follows at 125% of rated capacity to confirm structural margin. The drum is inspected for wire rope fleet angle and grooving. Motor housing, gearbox sump, and pneumatic control valve get visual inspection for leaks and seal condition. Only after every test passes does the unit receive its certification tag and ship to the field. Annual retesting repeats most of the same checks at the site. Hardness numbers separate steel that survives 10 years of abrasive wear from steel that fails inside a month, and you cannot tell the difference by looking. Portable hardness testers based on the Rockwell indentation method bring laboratory measurement directly onto the factory floor. The probe presses an indenter into the test surface under a defined load. Indentation depth gets measured in micrometers. Deeper penetration means softer material. Shallower penetration means harder material. Results convert automatically into Rockwell B, Rockwell C, Brinell, or Vickers scales depending on the standard the inspection runs against. Surface preparation is critical. The sample surface must be level, flat, smooth, clean, and meet a maximum roughness of 2 microns for accurate readings. Sample thickness must be at least 10 times the penetration depth. The instrument handles pipes, cylindrical samples, rolled metal sheets, steel coils, and the heat-affected zones beside welds, areas where in-lab destructive testing would be slow, expensive, and often impossible because the part cannot be cut for analysis. Annual factory calibration keeps the readings traceable. Every ton of TMT rebar that leaves a steel plant has been pulled until it cracks. At least one sample from each batch reaches the breaking point on a tensile testing machine. Proof the production behind it actually meets specification. A TMT rebar facility growing to 150,000 metric tons annual capacity sources scrap iron sorted by powerful magnets, then melts it in induction furnaces to burn off impurities and produce clean molten metal. The molten steel enters a continuous casting line running PLC-controlled automatic feeding, automatic cutting, automatic counting, automatic lubrication, and overload protection. Billets exit the caster, enter a secondary cooling chamber for full solidification, then reheat to recrystallize and reduce material losses. Rolling mills reduce cross-section by passing the metal between counter-rotating rollers until the final rebar profile emerges. Every lot then runs full testing, tensile strength, chemical composition, ductility, and more before shipping. Every ton of TMT rebar that leaves a steel plant has been pulled until it cracks. At least one sample from each batch reaches the breaking point on a tensile testing machine. Proof the production behind it actually meets specification. A TMT rebar facility growing to 150,000 metric tons annual capacity sources scrap iron sorted by powerful magnets, then melts it in induction furnaces to burn off impurities and produce clean molten metal. The molten steel enters a continuous casting line running PLC-controlled automatic feeding, automatic cutting, automatic counting, automatic lubrication, and overload protection. Billets exit the caster, enter a secondary cooling chamber for full solidification, then reheat to recrystallize and reduce material losses. Rolling mills reduce cross-section by passing the metal between counter-rotating rollers until the final rebar profile emerges. Every lot then runs full testing, tensile strength, chemical composition, ductility, and more before shipping. Quality testing isn't only for end products. The tools that maintenance crews carry into the field every day go through the same scrutiny, because a grinder failing in someone's hand inside a confined space is one of the worst hazards in industry. Compact angle grinder production at a German plant consolidates design, motor production, and assembly under one roof. Each tool is fully assembled by one operator who owns responsibility for that individual unit. Final testing is mandatory. Every grinder spends its first minutes of operating life in a run-in chamber under load conditions, followed by extensive end-of-line inspection. No tool ships until it has cleared the full testing protocol. The safest mode of mass transport in modern history achieves that record for one reason. Maintenance is treated as critical, not as an afterthought. The same principle governs every motion system in heavy industry. Aircraft maintenance, repair, and overhaul, known as MRO, runs on more than 4,000 certificated facilities in the United States alone, employing close to 200,000 people. Worldwide, roughly 4,700 facilities employ about 473,000. 4 times more people work at U.S. certificated repair stations than as mechanics directly employed by airlines. Most are family-owned specialist shops with under 50 staff, working on landing gear, avionics, auxiliary power units, and even cabin seat belts. Airlines contract maintenance out because specialist shops invest in training, tooling, and quality oversight no airline could match in-house. Every removed component carries traceable inspection records back to its last overhaul. Regulators audit operations continuously, and every procedure is fully documented before it gets approved. The toughest test of any motion system isn't on a load rig. It is the production shift the system runs every day for years. Operators report easier work, less bending, less back strain, while daily bale output rises. That is what proven in-service performance looks like. Thanks for watching. We're working on a few breakdowns that go even further than this one. Turn notifications on if you want to catch them when they land.